In today's video lesson, we're going to learn how to solve a calorimetry problem, and then we will do a sample question from one of the older AP chemistry exams from their free response. So we're going to start with the video lesson about what calorimetry is and how to tackle a calorimetry problem. So the problem we're going to look at specifically is dissolving a salt compound in water. And there's actually lots of different types of calorimetry problems. So just keep that in mind. We're only looking at one type of calorimetry problem in today's video. Okay, so let's look at the diagram I have here. What I have here is a beaker of water. Okay, so this represents water. And what I'm going to do is I'm going to dissolve a salt. So it could be anything, sodium chloride or any kind of ionic compound. We're going to dissolve this in the water. So I'll label this as the salt. Okay, so this will go in the water and dissolve. And when that salt dissolves, I want to be able to do a calculation to determine what was the enthalpy change, or in other words, the energy change that resulted from dissolving this salt in water. Okay, so it could be endothermic or exothermic, but what was that energy change? That's what we want to try to calculate. Okay, now when you dissolve the salt in water, the water actually represents my surroundings. I'll just label it as SURR, or surroundings. So what I mean by that is it's the medium I'm using to dissolve my compound. So as you can see, I've got a thermometer in the water. So I'm measuring, like as I dissolve the salt, I'm measuring what happens to the temperature of the water. Does it increase or decrease? How much water do I have? All of that represents the surroundings. So there's a formula I can use. After I dissolve the salt, I have a formula, Q of the surrounding, or heat of the surrounding, equals mc delta T, in which m is the mass of my surroundings, c is the specific heat capacity of my substance, which in this case is water, and delta T is my temperature change, or final temperature minus initial temperature of that water as I'm doing that reaction. Okay, now that's great, but if I go back to what I was saying earlier, I want to use this information to figure out how much energy was either released or absorbed by the compound. And right now I'm getting my answer for the surroundings, or the water. So we can convert backwards and use other formulas to help us figure out, in the perspective of we'll call the salt my system, or the reaction. So I'll abbreviate this RXN. We can use another set of formulas to kind of go backwards to determine, in that perspective of the system, what was that energy change? Okay, because this formula will tell me the perspective of the surroundings, and we can go backwards and figure out the system. So there's a formula, QRXN, or the Q of the reaction, will equal the negative Q of surroundings. And what that means is, if the surroundings, let's say if the surroundings got hotter and the surroundings absorbed heat, the reaction would have lost heat, right? So that's just like the law of conservation of energy, right? That the energy is transferring from one substance to another. And then from Q of reaction, we can calculate this into enthalpy, which I'll abbreviate as delta H of reaction, and that equals Q of reaction over moles. And so from these formulas, we can basically, by dissolving a salt in water, by determining what's happening in the water, we can kind of go backwards and figure out what was that overall heat transfer or enthalpy transfer in the perspective of that compound. So, okay, hopefully that makes sense. It's a lot of theory. So let's put that into practice by doing a sample problem from the 2019 AP free response chemistry exam. So in this question, let's just kind of look at question A. We want to measure delta H solution for lithium chloride. And to do that, a student added 100 grams of water, and they measured temperature change. So they're putting this in a calorimeter, and they see that the temperature goes up to 35.6 degrees Celsius. And by the way, they put 10 grams of the lithium chloride into the water to dissolve. So we have to do a couple things in this question. We're going to calculate the magnitude of heat absorbed by the solution during the dissolving process. And then we're going to then calculate delta H of solution. So delta H of solution is another way to say the enthalpy of the reaction. Okay, so in terms of step one, or part A, how much heat was absorbed by the solution? So that actually is my Q variable, Q of surrounding. And remember, it has the formula Q equals mc delta T. Now, in this question, we have to be very careful because there is some nuance and subtlety to these questions. We have to figure out, what mass do I use? Okay, so when I plug these variables in, we have to be super careful because I'm using 10 grams of the salt crystal, and 100 grams of the water. Now, if you guys remember, I told you that the water is the representing the surroundings. And so in some questions, depending on how it's worded, I would only use the 100 grams of water as my mass value. However, if I read this question very carefully, it says here, I need to look at the heat absorbed by the solution during the dissolving process. So the solution is the water plus the salt. So that's the lithium chloride. So in this question, I'm going to use my mass value of 110.0 grams. Okay, and remember that in some, depending on how this is worded, in some questions, if it just said the water, like the heat of the water, or if it just said the surroundings, you'd have to read between the lines to determine when do you add up these masses and when do you only use the water's mass. Okay, that's a really important subtlety. Okay, so I figured out my mass. The C value is the specific heat capacity that's given to me. So it's 4.18 joules per gram degree Celsius. And then the temperature change, remember, it's final minus initial. So final temperature 35.6 degrees Celsius minus initial temperature 15.0 degrees Celsius. Grams will cancel out. Degrees Celsius will also cancel out. And that will give me my answer in joules, 9,470. Okay, now I'm actually going to convert this to kilojoules because when we do part 2, delta H, the standard unit, is kilojoules per mole. So if we change this to kilojoules, this will equal, we move the decimal 1, 2, 3 to the left, 9.470 kilojoules. This is a positive answer. So this means it's actually an exothermic reaction in which heat is going from the system into the surrounding. Okay, so the surrounding is getting warmer in this case. Okay, now to determine delta H solution, remember, it equals Q of reaction over mole. Okay, so we have to do a little bit of work on this side, or you can kind of do this in your head, I'm sure, but Q of reaction is going to equal negative Q of the surroundings. Okay, remember from the formulas we looked at before. So Q of reaction is going to equal negative 9.470 kilojoules. And then I need to figure out how many moles I have of my compound lithium chloride. So I'm going to use a mole formula. Okay, I'm just going to call this my aside, kind of side work here. So the moles equals mass over molar mass. And just be careful, it's not the moles of the water. Okay, it's not the water. I need the moles of the compound because that's the system I'm kind of referring to here. So the moles is going to equal 10 grams over the molar mass of lithium chloride, which is 42.39 grams per mole. Okay, and that will give me a mole value of 0.236 mole. Okay, and this is lithium chloride, just to be specific. Okay, good. Now that I have my Q of reaction and my mole value, I can substitute these values into my enthalpy equation, and we can solve for our enthalpy of solution. So it'll be negative 9.470 kilojoules over 0.236 mole. My answer will be a negative value. It will be negative 40.1 kilojoules per mole, rounded to 3 sig digs. Okay, so we'll call this delta H solution. And that's my final answer. So again, this makes a lot of sense. That remember, this is exothermic. So the negative means that your system is, that actual compound is losing energy. And then the positive surrounding value means that the water, so the outside surface or the surrounding component, gained energy, and that both of these values represent an exothermic reaction. All right, please leave any questions you have in the comments. And it is a complicated topic, as well as just kind of understanding what variables to use. But I hope this helps you solve a problem like this for now. And thank you very much for watching.